this is Ito calculus 2, the last version of Ito calculus that is needed for finance, and that ends your third week's lecture. So, we have one more week to go, 5 more lectures to go, okay. And then we are first, let us just go back and let us see how Ito's formula can help you to compute the Ito integral. So, we have computed the Ito integral, if you remember in our last to last class, we have actually computed this integral. And we have written this as half but you know this can come out just right out of the Ito's formula, because if you take f to be fx to be equal to half x square, then half of w square t is f of wt minus f of w0, which is 0, and f of 0 is 0. So, here x square is, and this by your formula should be 0 to t f dash wt dwt plus half of 0 to t f double dash wt dt. So, what is happening here? So, we will just, we know that this is nothing but wt and we know this is 1. So, we will have half w square t is equal to 0 to t wt dw, sorry wt wt dwt plus half of 0 to this 1, so this half of t. So, you immediately know that if I bring it this side, I get this formula. So, it comes out of Ito's formula that we have studied. So, now we are going to define something called an Ito process. We have just mentioned in the last class what an Ito process would look like. So, an Ito process would look like the following. So, an Ito process xt, a stochastic process, consists of x0, which is the 0th value of this, which is non-random, plus an Ito integral so you have a stochastic integral and then you have an ordinary integral. So, this will be non-random, a number, this will be 0, I mean if you have w. This will be a number plus a random variable. So, basically it represents a stochastic process. So, xt is a stochastic process where theta t and delta t and theta t are processes or stochastic. We are not writing the term stochastic process every time, just write process. Are processes adapted to the filtration ft associated with the Brownian motion wt. They are adapted to the filtration ft associated with the Brownian motion. Okay. Now you know you can write this in a shorthand form. The shorthand form is, let me write, shorthand form or the stochastic differential equation form is DE form. The shorthand form or the SDE form would be of this type. You can write this as d of xt is equal to delta u dw plus theta u du. Most of the models that we will use in finance would be represented through these sort of shorthands. But please understand that this is nothing but a shorthand to this, because we essentially talk about Ito integrals, we do not talk about differentials of Brownian motion. Okay. One of the key formula that one now needs to talk about, what is the quadratic variation of this process. So, in this Ito world or the stochastic world, quadratic variation is a major player. So, you really have to talk about quadratic variation. What is the quadratic variation of this process? So, that is something that we should know. So, we will take two approaches to know about this quadratic process. First, I will give you the easy approach, then I will give you the actual approach. So, let me give you the easy approach first. So, we claim this. So, we write xxt and let us see what we do. Let us do the magic. The magic is we write the short form. Then you do dxt, dxt, and you use these things that we have written earlier in the last class. So, what you have if you do this, you have delta square u dwt dwt plus delta u theta u dw, sorry dwt here, sorry t here, t dwt plus, so basically it is 2 delta t theta t dwt, just you are doing squaring a square plus b, a plus b whole square, and then you are writing this as theta t square dt dt. So, this dwt dwt, this, and you know dwt into dt is 0, cross variation is 0, second variation of an ordinary function is 0, and but the second variation of a quadratic function is t. So, you have dxt dxt is equal to grad square t dt, and this is nothing but 0 to t. So, this is immediately, so this is nothing but the short form of 0 to t grad square u du. Okay, I could possibly go by the more deeper thing. Always know that when you are talking about Ito integral of a general function, you should always assume, sorry, this is always strictly less than plus infinity. Here the expected value of the of this integral of the basically L2 norm of this integral, this is a process. So, it will depend on t. So, this will also become a process. So, the expected value of that random variable depending on t has to be strictly less than infinity. That is the requirement, because that requirement will actually help us write that the difference between the simple process and the continuous process, when delta n minus delta t whole square 0 to t expectation, that limit would go to 0. So, that sort of thing is there. So, we do not get into all these things, we will assume that all these requirements are taken care when we are talking about this Ito business. Suppose we are now going to write down formally this process, this is a shorthand process, you might say, so this is some sort of a backhand stuff. So, maybe you will enjoy doing this backhand stuff a lot more later on, but we will do this backhand stuff later on, we will not get into writing too many things. But if I do the whole thing, then what I should do, you should let me write down IT, the Ito integral, as and RT so if these processes are continuous in terms of u, then by from simple calculus, from basic calculus, you know both of these are not these, this is already separately known to be continuous, but this you know would be continuous. So, IT and RT are continuous functions in T. So, these both are continuous and then you can write the Ito process xt as x0 plus IT plus RT. So, if you are going to write about the quadratic variation of this thing, then you are going to actually write, I will write in more detail possibly, you are essentially going to compute the following, the sampled quadratic differences, or which I should I do not know, I think it is called just give me a second, I will just tell you the name, I tend to forget this name, it is called the sampled quadratic variation of depending on the path. So, this I will write as x of t j plus 1 minus x t j, where the partition is as before. I am not writing the partition every time because that is boring to write down the same thing over and over and over again. So, now you know what does this mean? This means x0 plus itj plus 1 plus rtj plus 1. So, x0 gets cancelled. So, essentially down here when you expand it as a whole square, you essentially get and so now this is just this one. Now, if I want to do something here, what would I get? That is the whole point. See this, if I then this will be the quadratic variation of the Ito integral, and that would give you this formula. So, this thing, so limit pi going to 0, summation j equal to 0 to n minus 1 I t j plus 1 minus I t j whole square actually gives you the, so the quadratic variation of the Ito process is nothing but the quadratic variation associated with the Ito integral. That's the key idea. So sorry, theta u du. So that is exactly. So this is nothing but the quadratic variation. So what would be these parts? These parts would actually be 0. That is something you really have to just, I will prove for this part and then you can prove it similarly for this part by looking at the continuity of the processes IT and RT. So let me just prove for this part. So what you can do, that this value rather than the absolute value of this term I think there is no need of talking about absolute values because this itself okay does not matter. So I can write that this is less than equal to because this is a continuous function. So this difference would have a maximum value over the possible j's. There will be finite number of such differences and hence I can write this to be less than equal to this thing into this summation this actually means I can write the whole thing as this one summation n minus 1 this sum goes out and you have sum of r tj plus 1 minus r tj. So then I can write this term as 0 to t j to j plus 1 tj to tj plus 1 theta dt or theta u du. So which I can write again as, because mod of the integral is less than the integral of the mod, using that idea, very simple fact about integration theory, I can write this as let me look at this part. So I will write this as summation j is equal to 0 to n minus 1 0 to t theta u du, sorry 0 t j to tj plus 1 mod theta u t. So that is less than equal to max of and we have assumed that, let us assume that this is positive, this is always finite. Then as norm pi goes to 0, sorry here I am making a mistake, as the norm of the partitions goes to 0, so the distance between tj and tj plus 1 vanishes, comes down very significantly, this mod goes to 0, but this is a finite number. So this will be finally as goes to 0, this quantity, whole quantity will go to 0, which will immediately mean that the norm of this whole square goes to 0, which will mean that the limit of this as norm pi goes to 0 is 0. So, finally, we will get that limit of norm pi going to 0 when you take the third term out, you take the it plus itj plus 1 minus itj out and do the same thing. How do you integrate? If suppose you are given an adapted process adapted to a filtration, how will you integrate it with respect to a Ito process? Means we are asking, suppose I give you a process, what is the meaning of this? This simply means instead of dxu, say 0 to t, so instead of what you do is 0 to t, you know what is dxu, it is gamma u delta u d double u plus theta u du, that is it. So, if you want to take a process adapted to the filtration of the stochastic process Wt, that is the Brownian motion, then the integration with respect to an Ito process is nothing but this 0 to t gamma u delta u dw plus 0 to t theta u du, sorry, theta u gamma u du, that is a mistake, theta u gamma u du. Theta u. Now, of course, the question comes, what if I then start talking about the Ito formula for an Ito process? Let us see what I can do. What is the Ito formula for an Ito process? So, that is what we, so I am just going to write the formula, not write the details. So, Ito formula for an Ito process. With this, we will end our discussion on the Ito calculus and then show you applications in the next coming classes and take you at and end up with the Black-Scholes formula, that which many people must be wanting to see. Ito process, Ito formula for the Ito process. So, assume you take the f with the same sort of assumptions in the like the last class, fx and ft are continuous and fxx are all continuous functions, the partial derivatives, and then Ito's formula for Ito process. Once we know this, see, it is just a repetition of what we have done. The key formula is that you should know, the whole thing is that the key fact is that you just should remember this, and also remember that most models in finance are Ito processes, Ito's formula for Ito process. So, in the Ito's formula for Ito process, it is the same thing. So, for any t greater than or equal to 0, if t is greater than or equal to 0, then same thing. Now, instead of Wt it is xt here, observe that. In the same formula I am just replacing. Instead of dWt I will now have dxt. Now, I had dt in the other case. dWt, the quadratic variation of dWt, dWt, which became dt, but here I will have dxx t, which is nothing but dxt. Okay. So basically I can write this, instead of writing like this, I can write this as dxt. Now you know you can still simplify the formula by knowing how to put in the stuff of the Ito process. Do not worry, examples will now flow in, as we will show that so many things in finance are actually Ito processes. You can model as Ito process. Sorry, for don't no dt here, that is a mistake. Plus so here I will break it up into two parts in the same way. So I will have 0 to t fx txt delta t dwt plus 0 to t, so sorry 0 to capital T fx t xt theta u theta t dt plus half of 0 to t fxx t 0 to capital T txx tt fxx txt, and dxt is nothing but delta square t dt. You see, so this is the Ito's formula for the Ito process, and with this we have covered a huge ground of stochastic calculus. Of course, we have not been completely rigorous, because if you need to be completely rigorous, there could be, then you need lot of lectures to do it step by step and being very rigorous at every step. So we have not gone into rigor, but just had some fun, but at the end getting the formula that you would require to actually study finance. So with this I will end today's lecture. Thank you very much, and we will start our next lecture very soon, on which is the last week of the course.